Hello, Jerry.
Hi, Jennifer.
Hi, nice to meet you here.
Nice
So
to
we
see
can
you.
so we can just begin our this session. It's great to meet you here. Okay. Next, our Jerry Peng will introduce how Splunk is using Pulsar IO. Jerry Peng is currently a principal software engineer at Splunk, and he is quite experienced in Pulsar. And now
Thank you, Jennifer. Hi, everyone. My name is Jerry Peng, and today I'll present on how we at Splunk are using Pulsar IO. So first, to go over kind of the agenda for my talk. Firstly, I want to provide some context for everyone, so I'll provide a brief overview of Pulsar IO. Then I'll talk about how Pulsar is currently, in general, used at Splunk. Then more specifically, I'll talk about how Pulsar IO is currently being used at Splunk. Afterwards, I'll talk about the Pulsar IO batch that we have implemented for a specific use case at Splunk. Subsequently, I will also talk about the improvements we've made to the Pulsar IO and functions framework that we have contributed back from Splunk. Ending the talk, I will briefly discuss the future of Pulsar IO at Splunk and the projects, and new features we plan on implement in the future. So to provide everyone an overview of Pulsar IO, what is Pulsar IO? Pulsar IO is essentially a connector framework to ingress and egress data to and from Pulsar. And that's kind of the core essence of what Pulsar IO is. And some terms here that I would like to define. What we call a source is basically an application you can think of that ingresses data into Pulsar from an external system. Did I get disconnected or something?
Oh, yeah, maybe it just disconnected just now. Never mind.
Yeah.
Just go on. Okay.
Let me share my screen again.
Okay.
Okay. So to continue, I was talking about a source in Pulsar IO refers to an application that ingresses data into Pulsar from an external system, and a sink is an application that egresses data from Pulsar to an external system. So a good question to ask is, why Pulsar IO? A developer can always say, why not, just allow people to create a custom application that basically reads from an external system and produces to a Pulsar topic, or vice versa, reads from a Pulsar topic and, sends the data out to an external system. Sure, a developer can always do that if they choose to write their own application. But the thing is, not everyone is going to be, super familiar or have the expertise to write such, applications, especially when they have to deal with problems like, where to run the application, what APIs should I use, and more importantly, how should I run my application, especially in a fault-tolerant and scalable manner. So these questions, are typical questions asked by a lot of developers when they try to write an application that, will write or read. And to be frank, it's not usually easy to solve those problems. And what we tend to see happen is a lot of developers basically spend a lot of their time invested in writing basically framework code that will allow applications to kind of run in a scalable and performant as well as a fault-tolerant manner. So that's why we kind of introduced Pulsar IO as an integrated solution, so that we can have all this framework support to allow developers to really focus on the business logic that they need to implement. So to go over some design goals that we've listed for Pulsar IO, the foremost is easy to use. So I want to kind of clarify, different roles I will be talking about. the previous role I talked about is a developer that's actually, implementing kind of some code using Pulsar. But, there are also another class of, I guess people interacting with Pulsar is just typical users, right? They may or may not, want to write any code when they want to kind of ingress and egress data. They might just want to run a simple command to basically say, look, I want to read from S3, or I want to write to S3. Let me run this connector to read from this bucket or write to that bucket, from this to or from this topic, right? So one of the things that we have really focused on is making things easy to use, and a lot of the features we built around Pulsar IO, such as concept of a built-in connectors. Typical users just wanting to use a connector will not necessarily have to submit any code. They will just have to run basically a command to run and execute these connectors. So one of the other goals we had in mind, this is more targeted towards kind of developers, is we want to have a good kind of developing experience, like I said before, for developers to really focus on the logic of just getting the data into Pulsar from an external system and not worrying about things like execution, scheduling, scaling, and fault tolerance. So we want to create basically a managed runtime that the users can basically write their code, and then the framework will figure out all these details of how to run it. Another important thing that kind of this inherits from the Pulsar Functions framework that I'll talk a little bit about how basically Pulsar IO is built on top of Pulsar Functions, is the flexible runtime. And really here is, a cluster admin can kind of determine what is the best type of runtime to run instances of a connector. Should I run them as threads? Should I run them as processes? Or should I run them as, basically pods in Kubernetes? The Pulsar IO framework and the Pulsar Functions framework all support these kind of different runtimes to give the end user, to give basically a cluster admin the flexibility to choosing what is the best kind of runtime for their deployment environment. And to an end user, just like wanting to run basically a connector, this will be kind of transparent to them. Let me briefly go over the APIs for Pulsar IO. It's very simple and straightforward. The source API just contains essentially two methods: open, which basically is called once initially when the connector first starts, or when a connector instance first starts, and you can do a lot of the initialization routines for your connector in that method. And then we have a read method, which basically allows the user to keep returning new records or new data that should be sent to Pulsar. And on the egress side, we have the sync interface, which, just like the source interface, has the method open, which allows the instance to do some initialization at first. There is a method called write, in which basically the topic in which the sync is reading from, data from there will be inputted into this method as a record. And then the developer can basically use this record, get the actual data or payload, and determine how he or she wants to write that data to an external system. Now let me kind of go over how the architecture of Pulsar IO looks like. Like I briefly mentioned previously, Pulsar IO is powered by the Pulsar Functions framework. Thus, it inherits all the features and benefits of the Pulsar Functions framework. I won't go into too much detail about the Pulsar Function framework, because that in itself, is a talk, and I would encourage everyone to go look on the Apache Pulsar website for basically how, an overview of how the functions framework, details of how the functions framework works, as well as, more links to other resources for the framework. But essentially, what the framework does is it creates a managed runtime for basically instances of, sources or sinks for if it's, kind of a Pulsar IO connector, or function instances if we're just running a function. And they can all be run on top of kind of the worker service that in this diagram here shows that it's running as part of a broker process. So this is one flavor of deployment in which all of these functions, sources, and sinks run on top of the worker service, which is part of the broker JVM process. There's also another deployment method that I will actually talk about, and this is actually how we deploy at Splunk, is basically deploying function workers or the worker service as its own cluster to run separately of the brokers. And like I mentioned before, there's a flexible runtime. So all these basically instances of functions, sources, and sinks, it could be running as threads, kind of as this diagram implies, or running as processes, separate processes on the same node. Or another deployment method we have is on Kubernetes. These can be deployed directly as pods to Kubernetes to run there. I won't go into too much detail about the benefits, but I've listed them here. Like I said before, the Pulsar IO framework, because it's built on top of the Pulsar Functions framework, it inherits all of kind of the benefits, all features and benefits of Pulsar Functions, such as deployment flexibility, execution flexibility, parallelism, which you can dynamically scale a function. Thus, you can dynamically scale a sink and a source, automatic load balancing, fault tolerance, monitoring, metrics, dynamic updates, and also access to the state API. And I've listed some additional references to the Pulsar IO framework here that I would encourage everyone to kind of take a look at. So now getting kind of to the more interesting part of the talk is talking about what we have been doing with Pulsar at Splunk. So let me just first talk about in general how Splunk, what the status of Pulsar is and how Pulsar is used at Splunk. So to give some brief background here, we've initially we at Splunk did some benchmarking, comparing, we did some due diligence, as you will, to compare, Pulsar against, various other technologies such as Kafka, Kinesis, and SQS. But in kind of the benchmarking we have done, Kafka is really the only other contender. Kinesis, SQS, their performance and basically cost is not even worth considering or even really comparing, because the performance is not there or the cost is too high. So we really kind of benchmark Pulsar on Splunk Kubernetes infrastructure against Kafka, and long story short, Pulsar did much better in many regards in terms of performance and also cost of ownership than Kafka. So it's not really a hard decision there for us at Splunk to basically say, look, let's consolidate all these various messaging technologies, all these queuing technologies, and let's just standardize on Pulsar. So currently, we are running Pulsar as a multi-tenant service that powers various internal products, services, and use cases within Splunk. And most importantly, kind of one of the cool platforms that Splunk is developing or putting a lot of resources to develop is this project or platform called Data Stream Processor, DSP. So Pulsar was also chosen to basically be kind of the message bus or the nervous system of the data stream processor. So previously in DSP, when it was running kind of in a cloud environment, it relied on Kinesis as the message bus, and on-prem deployments, it relied on Kafka. But now, since we're using Pulsar, we were able to unify both our basically on-prem in-cloud runtime as well as an on-prem runtime to basically just use Pulsar. And from there, a consolidation story that saved a lot of, operation cost and engineering cost to support one platform instead of multiple platforms. And there's, that in itself, our journey with Pulsar at Splunk, that in itself is, a very long talk. And my coworker, Karthik Ramasamy, has, a great set of slides that he's presented at many conferences of, basically how at Splunk we transitioned to Pulsar and, all the benchmarking details and numbers that we have collected when comparing, Pulsar and Kafka at Splunk. So I would encourage everyone to, get more details from those set of slides. So now to talk about, let me go back. So now to kind of talk about something more in detail, this DSP platform that I mentioned before, because it has kind of relevance to how Pulsar IO is being used at Splunk. So let me just briefly go over kind of the architecture of DSP. So the architecture of DSP is depicted in this diagram. We have various basically data sources coming in from HEC, S2S, which are Splunk proprietary protocols, and also various conglomerate of sources that we call kind of batch sources here. There's also streaming sources that basically feed data into Apache Pulsar, a message bus, and from there, we have a stream processing engine that we use, i.e. Flink, basically that reads from Apache Pulsar, read from topics, transforms the data in topics, potentially writing it to another topic, and then eventually exporting that data to Splunk Index or another external system. So kind of how we are using Pulsar IO at Splunk is we have developed this kind of universal connector framework called the UCF, or Unified Connector Framework, as a platform to basically consolidate all the various types of connectors we have under basically that will be executed on one single platform that is basically powered by Pulsar IO. UCF is essentially designed, to run all types of flavors of sources, sinks, and to be basically have a common and core, common execution engine. So UCF was, an effort basically to replace the homegrown platform called LSTC, Large-Scale Data Collection. There was a lot of kind of, problems with LSTC that I'll talk about, in the subsequent slide, and why we basically kind of made the decision to transition from a homegrown kind of solution onto using Pulsar IO and leveraging open source. But here is kind of the eventual architecture, the architecture of the universal connector framework, in which we have all these kind of different data sources, and we have basically build connectors for all of them that run on top of this UCF framework powered by Pulsar IO that basically ingests data into DSP, as well as on the other side, we have all these sinks basically that implemented on UCF that will also egress data out of DSP. Just to talk about kind of why Pulsar IO was chosen, right? Why there was an existing kind of solution that was built in-house, and why kind of that was sunset. So there are some inherent issues with the homegrown system LSTC, as I mentioned before. There is not going into too much detail, but the architecture was complex. There were scalability issues, performance issues, infra costs. And the reason, the system was designed to be almost kind of like a map reduced type of system, in which it was to go out and discover data and then collect it. And one of the key issues with it is that, since we're running on Kubernetes, it had a long, basically, startup cost in terms of it, because spinning up pods in Kubernetes is not exactly one of the strengths of Kubernetes, the time it takes to spin up pods. Sometimes it can take, a good amount of time to basically, spin up pods in Kubernetes, as Kubernetes is kind of a platform built for long-running, processes or services, and not these kind of short-lived, process tasks. And another kind of more important thing is, look, like we're already using Pulsar, why not leverage more of its functionality? The costs and risks of maintaining a homegrown proprietary platform and all of that, especially when you're looking to hire people, no one's going to know how your proprietary homegrown platform works. But people might know how Pulsar or Pulsar IO works and have some experience with that. And another kind of rationale is, let's leverage some open source connectors, right? We've already implemented in open source community quite a few connectors. Let's see if we can leverage that, and also to engage with community, right? We're part of a data stream, building a data stream platform. Let's engage with the community and thought leaders out there, and be part of the conversation there. So let me go into kind of a little bit more detail about the use case at Splunk. So one of the key use cases is large-scale data collection. That's what was the name for the previous homegrown platform to collect large amounts of data. So when I say this, I'm not really talking about collecting streaming data or collecting data from, for example, ingesting data from, another Pulsar cluster or Kafka cluster or Kinesis. We're talking about basically collecting static data, ingesting them into DSP, which more specifically is just writing to a topic, a Pulsar topic underneath. So this kind of data would typically be something like that users would dump into an object store like S3. Like one of the typical use cases for LSDC, large scale data collection, is to read basically large amounts of objects from things like S3 or Google Cloud Storage and so on and so forth. So some of the requirements for basically collecting that data, we expect to ingest petabytes of data per day among customers, and run tens of thousands of connectors. And also one of the things that especially is important is the low startup time. We don't want to take 5 minutes to just basically spin up these connectors, as a lot of our kind of alpha customers have complained about that, in the previous legacy platform, LSDC, it took a long time to spin up all these pods in Kubernetes. And also it was, not very effective, not cost effective from that point to spin up a lot of, basically extra pods to run and then, kind of tear down. So this is where, we've also implemented for this kind of large scale data collection the concept of a batch source in Pulsar IO. So previously, like I discussed, right, there was the source I mentioned before, the existing source interface I mentioned before. That's more kind of tailored towards reading streaming data, right? It had basically an open method and a read method, in which the open method probably will go out and reach out to the external, message bus or external system, go figure out what data needs to be read, and then based on kind of its own instance ID, kind of create a hash of basically what portion of the data that this particular instance is responsible for. So that's kind of the workflow that's kind of the workflow that's targeted towards that flavor, that the original source and the original source interface in Pulsar IO. But to basically more tailor Pulsar IO for this kind of workflow, in which we basically want to go out and discover the data and then collect a lot of data in parallel, we've designed basically and implemented this concept, this new type of source called a batch source. So like I said before, in LSDC, there was like kind of two phases, right? Like discovery and collect. So we did basically carry over those concepts into our batch source for Pulsar IO. So in the discover data phase, we basically go out and discover the data that we need to kind of collect and ingress into Pulsar. And this phase basically, it reaches out to an external system, figures out what the overall data that needs to be read, and basically produces a stream of tasks for the collect phase to execute. So one of the special things, one of the special things about kind of the batch source is that its discover phase is only run on one basically instance. This is kind of in contrast with the streaming sources that was originally in Pulsar and Pulsar IO, in which basically each open method you can think of as an individual discover phase, in which each instance will run basically that open method and go reach out to an external system to kind of just figure out what is the overall data that that needs to be ingested into basically this topic, and what is the portion that I am responsible for. But now basically, instead of everyone call every instance of this connector calling to an external system, this is an optimization for basically the batch source, is that only one instance goes and reach out and discovers basically all the data, and then basically distributes that as tasks for other instances of the connector to execute on. So there's a rationale why we kind of made this optimization, is to reduce the number of redundant API calls, right? Like I mentioned before, and in the original connectors, each open method will likely have to reach out to the external system, and that creates kind of like a series of problems, especially if you're interacting with an object store on a public cloud like AWS, which will enforce rate limits on how many times you can call certain APIs to figure out what's in a bucket and so on and so forth. And they also kind of charge per call. So basically, having the discover done in one location is an optimization to kind of overcome these issues. And like I mentioned before, that after the discover phase can run basically in parallel at the same time as the collect phase, but the collect phase is basically the phase in which after a connector basically gets after an instance gets a task, it will execute that task, which likely is to go fetch some data from an external system and write it to Pulsar. And all in the collect phase, all the tasks are executed in parallel among the instances of the connector. So this is kind of the architecture of the general workflow of a batch source. There is typically a trigger that the user can also implement, but for example, it could be a cron trigger, say, I want to discover every 5 minutes. So batch sources have a more periodic nature, while kind of the original sources in Pulsar IO, more tailored to our streaming kind of paradigm, is basically always looking for new data. But as a batch source, it's triggered periodically to basically discover, write tasks to a task queue, and then all the instances will read from this intermediate Pulsar topic, which is the task queue, and basically read from this topic using a shared subscription, or basically using it as a queue, a task queue, read tasks off, execute them, and write it to a subsequent topic. So just to kind of briefly go over the batch source, just like the streaming, just like the original source, there's an open method that gets executed in the beginning. But the additional methods here is discover, which is the discover phase. It gets executed only on instance 0, on one instance. Basically, it takes in as a parameter as a consumer, in which the implementer can basically consume tasks that will be written to the intermediate topic or the task queue topic that will be read by other instances. And there's a prepare method basically that will get executed once an instance gets a task, and then there's a read method to basically say, look, I am going to execute this task and read the data. And when I'm done reading basically data, executing this task, and done reading data for this task, just return a null to signify I am done with this task. And there's also, if a user decides to choose to implement some sort of trigger, he or she could basically implement this batch source trigger to trigger kind of the discovery however he or she wants. And just to kind of talk about, as I mentioned before, how we are deploying Pulsar IO and Pulsar Functions at Splunk. So this diagram here demonstrates kind of our deployment strategy, and we're deploying everything on Kubernetes. But instead of actually running instances of sources and sinks as individual pods, we elected to run them as just threads in a cluster of workers that we deploy separately of brokers. So this is done to like I mentioned before, to address cost issues, as well as to minimize kind of the startup time of these connectors as well. So as you would imagine, running threads is relatively cheap, and it has a cheap, basically has a lower overhead than running processes, and lower overhead than running individual pods for each instance. And the reason kind of why we can, run, threads as just part of the JVM process of the worker, usually, there's probably security, considerations to that if you're, running arbitrary user code. But in our case, we're not really running arbitrary user code that some user is submitting. We're really running connectors that we have built, that we have vetted. So we deem as, safe code. Thus, we can kind of take advantage of basically running the instances as threads, which has a kind of a cheaper infrastructure cost. And to make our connectors be able to access state, we also run the table service, which is a feature of a bookkeeper, in a separate cluster as well, so that each source or sink can have access to end state. So now at the towards the end of the talk, let me talk about kind of the improvements we have made for Pulsar IO and Pulsar Functions, and have contributed back to community. So obviously we've contributed the bash source back to community that we use currently to power a lot of our use cases in DSP. We also, as part of we've done a lot of performance testing on Pulsar IO and Pulsar Functions, so that we can basically validate if the framework can support the number of instances and the ingest rates and the throughput that is required for data stream processor. So through all these performance testing, we're running basically hundreds of thousands of instances, ingesting petabytes of data a day. We discovered some bottlenecks and some architectural flaws in Pulsar Functions that we have since now fixed and contributed back to open source. I will discuss a little bit more in detail in my subsequent slides, but and we also have been just contributing a lot of bug fixes as well to make the platform more user friendly and stable. So to briefly talk about some of the major improvements we have made to Pulsar IO at Splunk. One is metadata compaction. Pulsar function original or previously the metadata topic, which holds basically a log of all the metadata function sources and sinks submitted, that basically grows unbounded and is not truncated at at any point in time. So obviously there is a red flag for us at Splunk, right? So we went and re-implemented how the metadata is re-registered in functions, and basically allowed the metadata topic to be compacted. We are using the topic compaction mechanism in Pulsar to basically truncate and only basically store the metadata as the metadata that is current and not basically expired. So you can almost think about how we use a topic as a key value store, right? In which a key value store in which there's also notifications for when a key is written and updated. So one of the other things we improved is there was a an issue with the scheduling and the assignments execution and functions. So the problem here is I guess you would need some context to Pulsar Functions, but for Pulsar Functions, but let me just talk about it really briefly, is that every single worker tails this internal topic called assignments to basically get assignments that the scheduler has produced and assigned to a specific worker. The problem what we notice is that very high number of instances, sometimes the scheduler doesn't sometimes the worker doesn't keep up basically with the scheduler, and in which basically there is also each worker has this tailer that tails this assignment topic to get the latest updates. So what essentially happens is this weird feedback loop that happens that a scheduler thinks that instances and that assignments hasn't been basically been executed, so I'll write more assignments, and this basically cascading effect of continuously writing more assignments to the assignment topic because the workers can't keep up basically executing these assignments. So what we fixed is we revamped the whole process of leader election, and basically when when the worker is a leader, which is also when the leader also executes or determines the schedule, it basically stops its own tailer and basically will execute because the leader will already know what the scheduling is. It will just execute the assignments that is assigned to itself. So we're not basically tailing basically assignments. The leader is not tailing its own assignments it's produced, thus basically fixing this feedback loop problem. Another key improvement is that we implemented, a rebalancing mechanism in Pulsar functions. Previously, there was no kind of rebalancing mechanism, and the thing we saw was, after running functions, Pulsar IO and the functions framework for a while, you notice that they will, eventually develop a skew, especially on Kubernetes when, pods can, die here and there, and scheduling gets, instances get basically scheduled to other worker nodes. But there's no way to kind of rebalance everybody so that, all the workers have kind of a fair share of work. So we implemented that mechanism for a user to not only be able to trigger that on demand, but also implemented an ability to automatically and periodically execute the rebalance so that, without user intervention, that all of the assignments can, be balanced. And if a user really wants to, implement its own strategy, we've also created an interface that can be implemented that a user or a developer could kind of implement how they want to do the rebalancing. And to talk about the future, work that we, would planning on doing for Pulsar IO at Splunk. So one of the things we are looking into is auto scaling, not only for workers, basically auto scaling workers as there's more load, but also auto scaling instances, right? So instead of a lot of this, instead of users having to configure the number of instances for a connector, maybe the user can just provide kind of an SLO or a service level objective to say, okay, I want this throughput at this latency, and there'll be an auto scaling strategy to basically say how many instances do I basically need for this connector. And another thing we're looking to implement is resource-aware scheduling. Currently, the scheduling doesn't take into account any resource usage, and we understand that different connectors probably have different resource usages, and to have the best type of scheduling so that individual workers will not be overloaded, we would be looking into how do we do kind of resource-aware scheduling for functions and connectors in the future, so that we won't have such a disparate kind of a possibility of a disparate resource usage among workers. And as we test some more and basically run Pulsar functions in the framework longer, we're going to contribute more fixes and optimizations that we see fit to implement. So that's the conclusion of my talk. Thank you, everyone. And like Jennifer said, if anyone has questions, feel free to reach out to me on Slack. I'm on the Pulsar Slack channel, open source Pulsar Slack channel. Feel free to reach out to me there about questions and about Pulsar functions, Pulsar IO, or Pulsar in general. Thank you for listening to my talk.
Thank you, Jerry. Thank you very much for sharing your expertise in Pulsar and Pulsar IO. I know that you are very experienced in Pulsar. Actually, there are some questions coming from our audience. The first one is, how do Pulsar cluster deploy? How is Pulsar cluster deploy on Kubernetes in Splunk? Are you developing your own operators or just manage clusters with hand?
Good question. I think that's, I would also encourage you to look at the slides my coworker Karthik has written. I think there's some details in there about this, but we basically have written our own operator for deploying Pulsar, deploying brokers, deploying bookies, deploying the function workers, deploying the table service, all of that, the whole life cycle, including, rolling updates. We've implemented our own, K8s operator to manage that cycle.
Another question is, how do you store data or how do you store broker data? Do you store it in PVC or in host path?
It depends on the environment. We do have because this DS data stream processor is a Splunk product, and it has one of the requirements is be able to deploy on-prem. So in terms of on-prem, a lot of what is leveraged is basically storing the data for bookies, obviously on the physical machines as well. But generally in the cloud, we would be leveraging PVCs, persistent volumes. I think I'm not too sure about the details, but I think even for on-prem, because we have our own Kubernetes installer on-prem. I think we use PVCs as well, but they map to actual data volumes on the underlying hosts.
Okay, thank you, Jerry. Actually, we still have a lot of questions on the waiting list. Maybe I can ask them to ask you in the Slack channel, or I can forward the questions from Asia in the Slack channel, and you can give them answer, and we can forward it to them. Because we are running running out of time for this talk, so maybe we can just stop here.
Sounds good. Thank you, Jennifer, and thank you, everyone.
Thank you, Jerry, and thank you, everybody. We have another new session, and you can just exit this one and enter the new session. Looking forward to see you again in another session. Thank you.
Thanks.